So let me show you how RSA works. And if you want to see the mathematics, please read the chapter. Okay. And the last exercise in the chapter gives you all the details. Okay. So RSA, public key cryptography. So the setup is the same. You have Alice who wishes to send a message to Bob, and Charlie is eavesdropping. Okay. And now before, Alice multiplied the message, okay, by some secret key K. So in the RSA cryptography world, Bob broadcasts public keys. Okay. And he broadcasts two things. One, a power, and two, a modulus. Okay, so let's take an example. Suppose Bob broadcasts the power 23 and the modulus 55. Okay. Now, corresponding to these two numbers that Bob broadcasts, these are called his public keys. He has what's called a private key. Bob has a private key, which is very hard to compute from the public keys. You basically, it's similar to the computationally hard reason why Charlie cannot figure out the birthday secret without knowing the secret K in the multiplicative model. So it's very hard to compute the private key. In this case, it turns out that Bob's private key is 7. Okay. So these numbers 23, 55, and 7 are very special. Okay. And one of the aspects of public key RSA cryptography is to actually figure out how to compute these numbers. Now I'll show you what happens. Instead of Alice multiplying the message M, so Alice has message M. Instead of multiplying the message M by some private key K, Alice multiplies the message M by itself 23 times. So Alice computes, M raised to the power 23, okay, in the modular 55 world. So she has to compute what this is equivalent to in the mod 55 world. Okay. So for example, if M is equal to 2, then Alice computes 2 raised to the power 23 in the mod 55 world. And you can go ahead and compute this using sort of techniques that I showed you here. And in this example, you would get that it's equal to 8. So Alice sends M star is equal to 8 across the channel. Bob receives 8. Okay, Bob receives 8, and Bob computes M star raised to his private key 7. In this mod 55 world. So Bob computes 8 raised to the power 7 is congruent to what in the mod 55 world. Okay. And lo and behold, you will find that 8 raised to the power 7 is congruent to, 2 in the mod 55 world. Okay. So you can go and do these exercises. And then you will see that, oh, wait, look, what? Bob has recovered 2, which is the original message M. So Bob has recovered M. Okay. And the magic of RSA is that Bob, with this process, will recover M no matter what it is. You can try it with 3, you can try it with 5, you can try it with 4. Whatever M is, Bob will recover M. As long as Alice raises M to the power 23 and computes the remainder, mod 55, and then Bob computes and Bob raises the message M star to the power 7, okay, and then computes the remainder mod 55. You will find that, this remainder that comes across the channel when raised to the power 7 will always recover the original message. And that's not trivial to prove. That's the last exercise in this chapter. Okay. Now what about Charlie? Charlie also sees 8, but because Charlie doesn't know the power to raise it to, basically cannot recover M. Okay. And why do we call this public key cryptography? Because the public keys Bob has broadcast to Alice and Charlie and everyone. So anybody can send Bob a message using these public keys. Bob is the only person who can decode the message. And fundamental to this entire scheme is the ability to raise numbers to very large powers. And fundamental to that is modular arithmetic. And here's an example of that. So play around with this and you'll see them. It's just unbelievable magic going on here. Okay, so today we covered number theory. Okay, it's a lot of stuff, but there's the fundamental facts of divisibility, GCD, Euclid's algorithm, Bezout's theorem, and applications of those. And then we move to modular arithmetic, which has the blockbuster application of cryptography. So if you want to end up in cryptography, you need to learn the number theory. So do all the exercises, do all the pop quizzes, and so on and so forth. Okay? For the moment, we're done. See you next time.